Hello everyone, let us continue the fourth part of today's class. Okay, in the third part we have taught to these slides. Okay, slides page 58. Okay, so for the first line, minus summation x p of x times log of p of x, it is the h of x, entropy of x. And for the second line, minus this term, minus summation xy p of xy log p of x given y. Okay, so according to page 56, x is equal to h of x given y. Okay, so it is equal to minus h of x given y. Okay, where the third step follows from the fact that log of p of x is only a function of x. Thus, the summation over the y component of the distribution is 1, leaving only the x dependence. Okay, let us see the third step. Okay, this is the first step. Okay, this is the second step. This is the third step. Okay, because log of p of x is not a function of y. So when we summation y only, the p of xy will become p of x and left the summation x. Okay, the second line in equation 2.11 follows directly from theorem 2.1. Okay, let us see the second line in equation 2.11. Okay, 2.11, the second line is this, is equal to h of y minus h of y given x. Okay, follows directly from theorem 2.1. Okay, let us go back to theorem 2.1. I of xy is equal to I of yx. Okay, because I of xy is equal to I of yx, so we can replace x by y, and x by y, and y by x, and we immediately obtain the second line of equation 2.11. So this completes the proof of the theorem 2.2. Okay, next let us see section 2.4, definition of Sisel capacity. Now that we have introduced some basic concepts and nomenclature from information theory, it is possible to define the capacity of a conventional Sisel communication system in a precise mathematical way. We start by recalling that I of xy, the average mutual information between two random variables, is the average amount of information about x that is conveyed by knowing the value of y. Okay, if we interpret x as the input to a communications channel and y as its output, as illustrated in figure 2.1. Okay, figure 2.1 is this figure. We have seen this figure earlier in today's course. Okay, back to page 63. Okay, then I of xy can be interpreted as the the average amount of transmitted information that is conveyed over the communications channel through examination of the received signal, that is Y. Okay, and the transmitted information is X. Although the communicators do not have control over the channel, the transmitter, in principle, does have control over the distribution of the random symbols it generates. P capital X of small x through its design of the information encoder. Based on these considerations, the capacity of a communication system is defined to be the maximum amount of information that is conveyed by observing the received signal Y, where the maximization is over all possible distributions of P capital X of small x. Mathematically, therefore, we define the capacity C of a SISO system as follows. Okay, you can see that there is a red rectangular behind this equation. So it means that this equation is very, very, very important. So the capacity C is defined as the maximum of I of xy. Okay, that is the average mutual information of x and y over all possible P capital X of x, small x. That is over all possible probability mass function of the random variable capital X, where the maximization is performed using the following constraints. First, 0 is smaller than or equal to P capital X of small x, and which is smaller than or equal to 1. Okay. Of course, it is because that the probability is always greater than or equal to 0 and smaller than or equal to 1. And summation x P capital X of small x is equal to 1. Okay. It is also obviously because the total probability must be equal to 1, which follow from the fact that these constraints apply to the distribution function of a random variable x. In the next section, we generalize the definition of capacity in equation 2.12. That is this equation for the case of a MIMO communication system. Okay, section 2.5, definition of MIMO capacity. First, let us see section 2.5.1, MIMO system model. We are now ready to apply the definition of capacity to MIMO systems. To do so, however, it is first necessary to develop a system model of a MIMO communication system. But what is a system model? Okay, if you have read some telecommunications paper, you should have seen this terminology, system model. Okay, determining a system model is very important for the research. For example, if you want to do research when you are in second years, in the second year of your master class, okay, to determine a system model is very important to you. Okay, but what is a system model? By system model, we mean a mathematical description of the relationship between the transmitted and received signals. We assume a narrow band signal, which means that the bandwidth of the communication signals are narrow compared to the coherence bandwidth. Okay, what is the coherence bandwidth? Let us see the handout. Okay, what is the coherence bandwidth? Okay, page 70. Coherence bandwidth is a statistical measurement of the range of frequencies over which the channel can be considered flat. Or, in other words, the approximate maximum bandwidth or frequency interval over which two frequencies of a signal are likely to experience comparable or correlated amplitude fading. Okay, what is the meaning of the word comparable? Okay, if you translate it to Chinese, it means 可比较的. Okay, but what is the meaning of 可比较的? Okay, that means the two things are similar in its size. 也就是说呢，两个东西它的大小呢是差不多的。Okay, this is the meaning of the comparable. Okay, coherence bandwidth of the channel, a concept that we described precisely in Chapter 4. We start by defining the following parameters. Hij is defined as the channel response between the jth transmit antenna and the ith receive antenna. Ri is defined as the received signal at the ith receive antenna. Sj is defined as the symbol transmitted from the jth transmit antenna. And Zi is defined as the noise at the ith receive antenna. Okay, it follows that Ri is equal to summation J is equal to 1 to Nt, where Nt is the number of the transmit antenna, and Hij times Sj plus Zi, where I is equal to 1 to Nr, and Nr is the number of the receive antenna. The receive antennas. Okay, Sj, let us review it. A symbol transmitted from the jth transmit antenna. And Hij, okay, Hij is the channel response between the jth transmit antenna and the ith receive antenna. And remember that at each receive antenna, it will receive the combination of all the signal times the channel response and its summation from all the transmit antenna. So J is equal to 1 to Nt. And Zi, okay, Zi is the noise at the ith receive antenna. So in matrix form, equation 2.14, this equation becomes a very simple form. Okay, R is equal to H times S plus Z. Okay, where S is defined as S1 to Snt transpose, and Z is defined as Z1 to ZNR transpose, and R is defined as R1 to RNR transpose, and finally H is defined as H11 to H1NT, and so on to HNR1 to HNRNT. Okay, when you see any vector and matrix, the most important thing at first, you must be very familiar with the dimension of this vector and matrices. Okay, for example, here S is an NT by 1 vector, and Z is an NR by 1 vector, and R is an NR by 1 vector. And please note that H is an NR by NT matrix. Okay, please note that H is not an NT by NR matrix. Okay. This system model is used throughout much of the MIMO literature and is used repeatedly throughout this course. Some authors reverse the dimensions of H so that it is dimensioned NT by NR. In that case, equation 2.15. Okay, 2.15. This equation, R is equal to H times S plus Z. Okay, becomes R is equal to S times H plus Z. Okay, and the vectors R, S, and Z become row vectors instead of column vectors. It is important for you to keep in mind the convention being used when reading the MIMO literature and to be able to switch between conventions. Okay, next let us see section 2.5.2 capacity. Okay, the capacity of a MIMO system is obtained by generalizing equation 2.12. Okay, let us go to equation 2.12. Okay, let us review it. The capacity C of a SISO system is defined as the maxima of the average mutual information between X and Y, and the maximization is over all possible P capital X of small x. That is, all possible PMF of the input of the channel. That is capital X. Okay, which is done by replacing capital X with the vector S and capital Y with the vector R. Using the relationship in equation 2.11. Okay, let us go to equation 2.11. Okay, equation 2.11 shows that the average mutual information between random variables X and Y, okay, I of X, Y is equal to the entropy of X minus the conditional entropy of X given Y, and is equal to the entropy of Y minus the conditional entropy of Y given X. Okay. Okay, we obtain the following expression for the capacity of a MIMO system. Okay, C MIMO is equal to the maxima of h of r minus h of r given s. Okay, and the term under the max is ps of s1 to snt. Okay, where s is the vector s, okay, which contains nt symbols s1 to snt, where the maximization is over the multivariate distribution ps of s. Okay, equation 2.20. Okay, let us go to equation 2.20. Plus, okay, this is an invalid hyperlink and I will fix it. Okay, equation 2.20 is this equation. Okay, C mimo is equal to the maximum of the entropy of R minus the entropy of R given S. Okay, equation 2.20 can be simplified using the fact that R is equal to H times S plus Z, which implies that H of R given S is equal to H of Hs plus Z given S. For a given channel matrix, Hs is fixed, so the only random variation in H of R given S is due to the noise term Z. Okay, so it follows that H of R given S is equal to H of Z, which means that the MIMO capacity simplifies to the following. Okay, C MIMO is equal to the maxima of the entropy of R minus the entropy of Z. Okay, and the maximization is over all the possibility of PS of S1 to SNT. In order to obtain a final expression for the capacity of a MIMO system, we need to evaluate the two terms, the entropy of R, that is the entropy of the received signal vector, and the entropy of Z, that is the entropy of the noise vector, in equation 2.21. Okay, let us go to equation 2.21. Okay, is this equation. We do that in the next two sections. Okay, so in section 2.6, evaluating the entropy of Z, where Z is the noise vector. Okay, we evaluate H of Z by assuming that each of the elements of Z are independent, identically distributed IID real Gaussian random variables with mean mu and variance sigma square. Okay, thus Z has a multivariate Gaussian distribution given by this equation. Okay, I do not know if you have seen this equation before. Okay, if you have seen this equation before, that is good. Okay, if you do not have seen this before, okay, let me teach you now. Okay, Pz of Z, okay, it is the PDF probability density function of the vector Z, is equal to 1 over the square root of 2 times pi to the power of nr, and the determinant of RZZ, and to the power of 1 over 2, and times the exponential minus 1 over 2 times Z minus mu transpose times the inverse of RZZ times z minus mu. Okay, where mu is defined as the expectation of z, and RZZ, okay, it is 25 minutes. See you next time. Goodbye.